So last time we talked about KSP and again some factors that really do affect solubility. So really last time again we covered common ion. We covered pH and also concentration, which again are three things that can affect solubility of a substance and can have an effect on the KSP. We also saw that you can use the KSP to do something like selective precipitation. And again, by really knowing the, for example, concentration of a precipitating reagent that you need, you can, as we saw in that example, precipitate out, for example, one ion and leave the other one still floating around in the solution. Then we turned our attention to another K value, which is Kf, which is the formation constant. And Kf is typically the one for complex ions. And complex ions are a metal that's typically in the middle. Usually it has a number of what are referred to as ligands attached to it. Ligands are Lewis bases, which means they will donate a pair of electrons to really our Lewis acid here, which is the metal, which is deficient in electrons because it typically has a positive charge in that case. So as I talked about yesterday, and as we'll talk about in a later chapter where we officially sort of cover in a little bit more detail, complex ions, it is more of like a Lewis acid base situation that happens in that particular case. One of the main differences between these two sort of values is sort of the magnitude of it. As we talked about with KSP, typically KSP values are relatively small because they're for things that are insoluble, and that means that they will stay on the reactant side and obviously not break apart as much. Here with KF, they are typically large values, and what that means is when we have basically the sort of situation where we can form a complex ion or we have a really good ligand involved, the formation of a complex ion is pretty much favored as it would want to go to the product side in this particular case. Because the Kf is typically a large value, we make a couple of assumptions when we do these type of problems. The first sort of assumption we make is that all the metal ion will get used up in the complex ion. So if you remember, where that really affects is, again, when we do our ice table and we get sort of our initial concentrations of everybody, we really don't use X's in this sort of table. We do use the actual number of the metal concentration as that should be used up. The second sort of part of that assumption is, even though we are essentially assuming that this reaction is almost 100% heading towards the product side, it is still a reversible reaction, which means even though, like I said, almost 99.999% of that metal ion is going to be trapped in the complex ion, a little bit of it will break apart and come back the other way because, again, it is in equilibrium going in both directions. So you will have a little bit of free metal ion, and the concentration of the free metal ion should end up being relatively small. If you remember, I think the example we did where we left off kind of previous to this, we end up with like maybe like 1 times 10 to the, or whatever it was, times 10 to the minus 18 or 13, a really, really small number. And that, again, is a way you can kind of check yourself in this situation because, again, that formation of that complex ion definitely is favored in this case. Any questions on that there? All right, so we were kind of in the middle of this example. You're working on it. Hope maybe you finished it, hopefully. If not, we're going to kind of start off here and kind of go through this one together. So one of the other things that we also talked about with these formation of these complex ions is the ligands are added one at a time. So it is a stepwise sort of formation of the overall complex ion. And in some cases, you are given sort of the overall reaction that's happening to make the completed complex ion. And in some cases, like we see in this particular example, we're given sort of the stepwise formation of that complex ion. So in this case, we're actually looking for pretty much everybody's concentration. We're going to mix basically 150 milliliters of 1 times 10 to the minus 3 molar silver nitrate with 200 milliliters of 5 molar Na2S2O3. We could get our overall reaction here by, once again, adding these guys together. And what we will see is we will actually cancel this guy out as it's on opposite sides of the arrow. And that will leave us really the overall reaction that we're looking at here, which is our silver plus a couple of the thiosulfates here. And that will form our complex ion on this case. And a reminder that when you do add equilibrium reactions together like this, when we want the, for example, Kf in this case, we do not add the K values, but we do need to multiply the K values. So here, if we wanted the Kf, we would take K1 times K2. And just to give us our sort of Kf here, that would then be, in this particular case, 7.4 to the 8 times 3.9 to the 4th. And I'll get us something like, we'll call it 2.9 times 10 to the 13, which would be our Kf value in this case. Again, a relatively large one here as we are forming the complex ion. Now, we do want to do an ice table here, and we really want to kind of do an ice table once we kind of mix everything together. Once again, here, the silver nitrate is going to be our source of silver in this reaction, and our sodium thiosulfate is going to be our source of the S2O3 2 minus. So I do want the concentration of both of those guys kind of together. So that is again going to be like an M1V1 equals M2V2 sort of situation. So if I wanted our sort of initial concentration once we mix them of silver, we would need to do that. So we'll go 150 milliliters times the molarity there of 1 times 10 to the minus 3 equals M2. And now again, our volume here is going to be a total of 350 milliliters as we took 250 plus 150 milliliters there. I think our 200 plus 150 would give us our 350 milliliters. So that is what we would use here for our V2, which would be our total volume. And that's going to essentially give us, for the silver here, 150 times 1 to the minus 3 divided by 350. And we're going to end up with something like 0.000429 molar. Again, we also want the concentration of the S2O3 2 minus. Here we are using 200 milliliters of this one. And the concentration is 5 molar. Again, we will have our total volume here when we mix them all together of 350 milliliters. And that's going to give us our kind of starting concentration here, really, of our other one. And it looks like maybe a 2.86 molar. First off, any questions on that there? All right, so since we're really looking for everybody's sort of concentrations, we can basically do an ice table with the overall reaction that's happening here. So that is what I'm going to do. So I'll take my overall reaction, which again is my silver plus my couple of these guys here. And that's going to give me my complex ion here. All right, so initially here we are going to use what we just calculated there for our silver, and I believe that was 0.000429. 0.000429. For our S2O3, 2.86 molar and 0. Once again here, because this is a complex ion formation, we also see our Kf value is large. We can make those assumptions that we talked about a second ago, and we are going to assume that even though this reaction is a reversible reaction, for all intents purposes, it is sort of going in a one-way direction towards the products. And that means our change here will be our metal ion, as it should be tied up in that complex ion. We do need to still remember to take care of the coefficient here. So as we talked about, that's basically like minus 2x. So we do have to take 2 times that value, as this number here is essentially x. And we do need to add this number to the other side. That means at equilibrium here, all of our metal ion here, which is our silver in this case, is going to be gone. That will leave us for our guy here next to it, essentially still 2.86. And at this point, 0.000429 molar. First off, any questions on the ice table here? At this point, I essentially have found 2 concentrations. We could see from this table that at equilibrium, the concentration of S2O32 minus is 2.86 molar. We also could see that the concentration of our complex ion is 0.000429 molar. So we got a couple of sort of answers here from just really the overall ice table and reaction that's happening. And if we look at our problem here, that means we essentially got this guy's concentration. No, we did not. We got this guy's concentration, DS2O4, and we got that guy. All right, so at this point, you have a couple of options. Since we are looking for everybody else's concentrations, we can do one of 2 things at this point. So I can definitely at this point use the individual stepwise equations to find all the other ones. And that's the approach I'm going to take first here. And what I would do at this point is, since I now have this concentration from my ice table, and I also have this concentration from my ice table, that will allow me to use the second equilibrium reaction here, basically to find the intermediate, if you will, sort of concentration. So that is what I'm going to do. So I'm going to use, in this case, the K2 reaction. And the K2 reaction, if we write our equilibrium expression for it, is the concentration of Ag S2O3 minus divided by our Ag S2O3 minus and our S2O3 2 minus. And that is going to equal, obviously, our K2 value there at 3.9 times 10 to the 4th. So again, a reminder that I am using this reaction here, and that is why I do not need to square this one, because I am not using the overall reaction here. So that is why that one is not squared, in case you have a question on that. We're going to put our numbers in here, and essentially, kind of similar. These 2 guys are going to switch places, basically, if you rearrange this correctly. And that will give you that the concentration of Ag S2O3 minus equals our equilibrium concentration of our complex ion divided by our K2 value that we moved over, and divided by our equilibrium concentration of our S2O3 2 minus. So putting that into this here, we will now get our value for really our intermediate here. And that is going to be something with a lot of zeros, it looks like. Let's see. That's going to get us here 3.8 times 10 to the minus 9 molar. Once again, if you're not in scientific notation, you probably got a bunch of zeros and a 4 at the end of your calculator, and that's okay as well. Any questions on that so far? Now, once I've gotten sort of that intermediate, I again really have a couple of options, but I'm going to choose now to use K1's reaction, because at this point I now have found this guy and I still have this guy. And that is going to allow me to get to silver at this point. So I could go to that individual reaction, and maybe I'll try to squeeze it in here and see how we do. So using K1's reaction down there, that's going to give us our intermediate that we just solved for, divided by silver, which we are looking for, and also our S2O3. And again, that is going to equal our K1 values. So putting in our numbers, again, these guys are going to switch places when you rearrange that. That will give us a silver concentration that is equal to what we just solved for, 3.8 times 10 to the minus 9, divided by our K1 value, which was 7.4 to the 8, it looks like. And again, our 2.86. Once again, I am using this equation here. There is no coefficient. So again, I'm not using the overall reaction. And that is, again, why I'm not squaring that one as well. And if I do that, I will end up with here. A silver concentration of 1.8 times 10 to the minus 18 molar. And again, that is sort of what we would expect, because we would expect the concentration of the silver to be relatively small, right? Based on our assumption. First off, any questions on any of those answers there? So that is one approach that you could do, and you can see, obviously, you could get your answers here by just using the individual stepwise reactions, because they're all equilibrium reactions, and you have equilibrium concentrations from our first ice table. They all could go in there and just use those. Now, if you wanted to, you definitely could have done this problem similar to what we kind of did in a previous problem. And what I mean by that is we can use the overall reaction, and we could use our Kf value here and actually get our silver first. So you could have got the silver first. So that's 2.9 to the 13. So 2.9 times 10 to the 13 is the Kf value that we got for the overall reaction. Just like we did previously, we could have just, after the first ice table, called this X and used now the overall reactions K. And if I did that, that will give me my complex ion. Divided by my silver and my S2O3 2 minus. Here I would need to square it, because I am now using this equation, the overall equation at this point, and obviously our overall K value that we found on the first page. So that would equal our 2.9 times 10 to the 13. We then can put it in there. So I think I'll flip it around there, 2.6.00049. So let me go here to this page, maybe rewrite it there. So at this point, we have our Kf is equal to our product, our silver. Go the wrong way. I did 3, 2, 3 minus 2. And our silver. And that is our 2.9 to the 13. All right. All right, so once again, we're going to swap these guys around, and that will give us our silver is equal to, we had 0.000429 divided by 2.9 times 10 to the 13. and our 2.86 squared. And if we pop that in there and we went this approach at the beginning, we should end up with our same value that we got on the other approach. And you can see you get 1.8 times 10 to the minus 18 molar for your silver. So again, you could have used the overall reaction and the KF value like we previously have done and went after the silver concentration first. You get the same answer. At that point, you then could go to either of these sort of reactions and find what was missing. You probably could have just used the first one and then found this guy's concentration by using the first one. So you could have took that approach and you should get the same answer. So you do have a few options if you're given the stepwise sort of formation. You could go into each of the individual ones. You could use the overall reaction, the overall K value for it as well. Any questions on any of that there? All right, so let's take a look at one more here. We want to calculate the molar solubility of silver chloride in 1 molar ammonia. And we have two reactions happening here. We got a KSP reaction, which is our silver chloride breaking apart into the silver ion plus the chloride ion. We also have our KF here, which is our formation constant of our complex ion happening. So once again, just like we did previously, we got kind of a couple of things happening. We could add these reactions together and kind of see what is happening. And in this particular case, it is actually the silver that's going to cancel out. And that will give us really the question there, which is what is the solubility of silver chloride when you add ammonia to it, right? And it's going to make this complex ion here and chloride. Now, if I want a K value for this, I again would, in this case, multiply the KSP times the KF. By the way, it doesn't matter that one's an SP and one's an F. They're all still equilibrium constant values. It's basically the same idea as when you take Ka times Kb, gives you Kw, so it doesn't really matter if they're equilibrium constants, whatever the little subscript is, you can multiply them together because they're basically the same thing in terms of how you get that. So if we do that in this case, we will actually get 1.6, we got there to the minus 10 times 1.5 to the 7. And that's going to give us a K value for this overall reaction of 2.4 times 10 to the minus 3 in this case. Now, in this particular case, we're looking for the molar solubility. So this is actually more of a KSP type of calculation than it is sort of a KF type calculation. And that's the approach we're going to take here. So we'll take our overall reaction here, which we just added, which gave us our silver chloride and our ammonia, making our complex ion and our Cl minus. And again, we got there for our K 2.4 times 10 to the minus 3. Now, if we look at the problem, essentially the only thing that's given to us is we are basically going to add 1 molar ammonia to this. So we are going to do an ice table, and we would have 1 molar ammonia. We will do this very much like a KSP table. These are going to be zeros because we have no mention, obviously, of anything else. Now, a little bit different because we're kind of comboing both of these together since we're still kind of doing a KSP type calculation. We normally do not have things on the left-hand side, but in this case, we do have ammonia, which is aqueous. So we do have something on the left-hand side. So this would be plus 2s. And I'm sorry, that would be minus 2s. Come here. Minus 2s there. So that would be minus 2s, and obviously on this side, plus s and plus s. Again, a reminder that s is our molar solubility, and that's essentially what we're looking for. We will come down here in this case, and this will give us 1 minus 2s, s, and s. Any questions on the ice table? Yeah. Yeah, it is included in this case. It is aqueous, and this is aqueous, and regularly this is aqueous. So it is included. It is actually like a spectator ion. So we do include it because we're not doing anything like pH in this case, right? And in pH, we wouldn't have to worry about it. But here we're looking for solubility, so we do have to worry about it. Yeah. Other questions? All right, so this is going to go into our equilibrium expression. And that also is why, right, at this point, we're really not doing anything with the solid here because it's not going to be included in the equilibrium constant, even though technically speaking, that is kind of what we're looking for in our final answer, but we're not going to actually include it here. So we will go with our complex ion times our chloride divided by our ammonia. And once again, here we do need to square it because of the coefficient. And that will equal our 2.4 times 10 to the minus 3. Putting in our values here gives us basically S squared on top divided by 1.0 minus 2S. And we again do need to square it equals 2.4 times 10 to the minus 3. So we do want to solve for S, which is our molar solubility here. Hopefully you recognize this. It actually is a nice little perfect square action happening there. So we can square root both sides. That will give us S divided by 1 minus 2S equals, and you don't want to forget to square root the other side there, 2.4 to the minus 3 square rooting. Going to get us 4 point, and we'll call it 90 times 10 to the minus 2. We're going to multiply that to the other side. Will give us S is equal to 4.9 times 10 to the minus 2 minus basically times 2 there, I think. And we'll go 0.09, and we'll call it 8 in this case. We are going, and that is S. We're going to combine our S's to one side, so we'll bring that over there, and that's essentially going to give us 1.098 S equals 4.90 times 10 to the minus 2. Obviously here dividing now to the other side, that will get us here a molar solubility, I'll just go up here, of 0.0446. And that would be the molar solubility of silver chloride in ammonia. So just to give us an idea in terms of grams, if we take the molar mass of silver chloride, that's 107.9 plus 3545. So if we take that there, 0.0446 moles per liter and multiply it by the molar mass of silver chloride from the periodic table, we will see that we will end up with about 6.3, we'll call it 6.4 grams, 6.4 grams per liter of silver chloride will dissolve in ammonia. Now, if you remember, we actually did at the very beginning of this chapter, silver chloride in water. And what we ended up getting was basically S squared is equal to 1.6 times 10 to the minus 10, giving us an S value of approximately 1.26 times 10 to the minus 5 molar. That was the molar solubility of silver chloride in water, which if we multiply by the molar mass of silver chloride, so we take that times it by the molar mass like we did in that first example. Remember, we got basically 0.002 grams per liter, yeah? So remember, in water, the solubility of silver chloride is 0.002 grams per liter. In the presence of ammonia, it's about 6.4 grams. It is more soluble in which one? It's more soluble in the ammonia, yeah? And that is again because the formation constant is very large. So whenever you have that opportunity to make a complex ion, it is definitely going to probably be favored because it definitely wants to make that. This is exactly what you did in the very last step there in group one when you added the ammonia to the silver chloride, right? Your silver went from the solid into the solution as part of that complex ion, right? That is essentially what you made when you did that step in group one. How did you know silver was there? You then added a bunch of strong acid. And when you added a bunch of strong acid, that protonated the ammonia, freed up the silver ion again. And who else was floating around? Chloride was still there, right? That allowed these guys to come back together. And that is when you saw your white solid reappear when you hit it with the nitric acid at the end. So that's exactly in this problem, basically what was happening there in group one, the very last step that you did. But again, this demonstrates definitely if you have a ligand, you can form a complex ion. It is definitely going to be favored in this situation. Any questions on that there? All right, well, they say that is chapter 15, I think. Here's a table of some KF values. Again, because as we've been talking about, very large, so they're very much usually favored. That is chapter 15. Any questions on that?